All right. Our goal is to talk about challenges in analyzing and optimizing parallel programs. Okay. I mean, let's start with some kind of history, right? The computers, I mean, the first computer, if you look at it, right? If you look at just the design part, 1842, Charles Babbage, right? The analytical engine. It took nearly 100 years to come with the first commercial computer. And in another 50 years, IBM Roadrunner touched the petascale limit. Does anyone know what's the fastest computer now?
Summit or Fugaku.
Yes, Fugaku. So in 2 years from petascale, we became to 10 petaflops. And 2020, Japan's Fugaku has nearly touched exascale, you can say, with reduced precision, all right, but it does. Okay, but in terms of with precision, it's around 400 plus petaflops, right? I mean, see, here the question. I mean, how much has the speed increased? If you look at from 1993, when this 286, 386, etc. started coming in, right? To 2021, actually it should be 2020. From 2020, it hasn't changed yet. The speed has increased by more than 6.4 million times. Right, the amount of performance flops we can derive. And as you can see, the increase in petaflops has a lot to do with the increasing number of cores, the amount of hardware parallelism that is coming in. Okay. There are also other factors, but a big factor in this is the amount of parallelism. I mean, the one question that we can ask ourselves is, when the parallelism is increasing, can we really take advantage of it? Okay, with every new hardware that we get, right? You see that pretty much every hardware is a parallel machine. Your cell phones are parallel. The laptop I have that I'm presenting in is a parallel machine. I mean, and the parallelism is increasing. There are also parallel languages that are being used to exploit this parallelism. CoreF, Fortran, Chapel, UPC, Extend, CUDA, OpenMP, MPI, OpenCL. You can increase the list, right? I haven't listed more general purpose languages like Java, Python, which also support threads and all that. See, you can always say, look, I know how to use a machine, I know how to run a program, and why should I change anything? Yes, you have a phone, you had a phone. If you want to use the new phone with the features of the old phone, then you will be severely restricted, right? You can say, look, if you want to play 2020 like test cricket, then again, the amount of, your success will be very limited. What's the moral of the story? Look, there are new challenges. The new challenges needs new solutions, right? So what are the new challenges? When we have new hardware, when you have new languages, right? Where the languages are, we are talking about explicitly parallel languages, right? The challenge is that the applications of the system software must be redesigned for multi-core parallelism. It could be via automatic parallelization. Okay. where the compiler takes a serial code and tries to parallelize it, or could be compiler takes some programmer help to serialize, a refactoring tool takes some programmer help to refactor some code, or you think and write in parallel. You think and write in parallel and ask the compiler to optimize the code. Okay. So the new challenges here would be, now we want to analyze or optimize such parallel programs. So if you look at your own architecture book or any book on optimization or Hennessy Patterson's architecture book, right? They will say the biggest overhead in any program is, if you want to execute a program, what's the biggest overhead? Anyone? Let's try to, I mean, I'll be, if there are questions, please ask back. I would also like to keep it interactive as well as possible. So what's the biggest overhead that we normally see in programs? Anyone?
In the software stack.
Yeah, in the software, if you have given an app.
Mostly it's like the serialized nature of tasks. Like
Right. If I give you a serial program, let's say, right? I give you a serial program. What's the biggest overhead in this? It does many operations, right?
it's kind of when even independent sections need to be executed in kind of in sequence, right?
Right. So given a serial program, what are the different components I access? One is ALU, the other is memory. So we can get some speed up in ALU, but the biggest overhead, as many of you would know in your mind, is memory, right? If I can reduce the memory access overhead, then my program, I'll get the maximum bang for the buck. In parallel programs, communication is the biggest overhead. Okay, communication as in you have multiple tasks running and multiple threads, and then when they want to wait, when they have to wait for each other, when they have to transfer data, they are kind of much slower than memory accesses. Memory accesses are slower, and the communication is much slower than memory access. Okay, so that's one very important challenge. The second important challenge when you want to analyze and optimize task parallel programs is coming from the language side. When the programmer writes a program, they can write in many different paradigms. They may be writing in data parallel programs. I as a compiler or a tool may have to optimize task parallel programs. I could have recursive task parallel programs where the parallelism gets unfolded in recursion. I can have irregular task parallel programs where the different parallel iterations may be doing very different amounts of work, okay, and which cannot be analyzed statically. So our goal is to understand the challenges in analyzing and optimizing parallel programs, and I promise I will not show traditional matrix multiply codes, right? Our goal is to look beyond traditional loops where the codes have been very well studied. Okay. The way I have organized the talk is that I will be proposing a few programming challenges type of things. From that, I will try to identify some patterns that can be analyzed and optimized. Okay. Any questions so far?
So what do you mean by communication here? Because communication can happen through memory. Yeah, it can happen even through registers. So
Right. Very good. Very good. Excellent question. See, when we are talking about parallel threads, right? So rather different entities executing in parallel. What they can be threads or processes. Okay. So neither threads nor processes share registers. So communication cannot happen via registers. For processes, the communication cannot also happen more via memory unless you are talking about something like DMA, direct memory access and all that, RDMA. Okay. Even then, even if you have such RDMA or even threads, whenever we are talking about communication, two things are involved. Let's say I have two threads which share some memory. The communication doesn't only require writing to memory, but also waiting for each other. I may have, let's say I have my post box and multiple guys can write to it to tell me something, but then they have to take a lock. Each one has to take a lock, and whoever gets the lock can write. The other person has to wait, may have to wait, right? So when we are talking about communication, it could be communication of data, synchronization among the threads and processes or tasks, creation of threads, joining of threads, creation of processes, joining of the processes, and so on. All these involve communication with among themselves and with the runtime. Okay. Very good question.
right, but that also involves the memory model, right? So
That
when you
involves memory. So what we are saying is the cost for communication is far more than memory, that of memory. So if you can reduce the amount of communication, see, if you speed up memory, sure, it will help. Of course, it will help. But the biggest overhead is communication. You just reduce communication, that gives you a lot of savings. On top of it, improve memory, it will further improve. On top of it, improve ALU related things, you'll get more performance.
okay.
Right?
So do we talk about any specific architecture?
No, so we are not talking about any specific architecture in this, but in general, I mean, if you look at x86 or some of these architectures, you will find that, or why only x86? Any of the MIPS architectures also, you will see that this ladder, fastest being ALU registers, then memory, then communication, that holds. Okay.
Okay, thank you.
Okay. Any other question? All right. Let's continue then. So I will be using a very simple syntax, and even though the syntax is from a specific language, you will see similarities with many of the programming languages you are familiar with. Okay. So I will use a keyword called async. What will async do? async and a statement. It could be a compound statement or a simple statement. Async S creates an asynchronous activity. Okay, so if I have some statement S1, then I have a statement async S2 and a statement S3, then S1 will execute. After S1 ends, async S2 starts, and what will happen? S2 will run in parallel with the remaining code, in this case S3. Okay. The second syntax I'll talk about is finish. What does finish do? It works as a join. So in this code, if you look at it, I have a parent task which executes a finish. In the finish, I'm executing S1. So after S1 is over, let's say S1 is a serial piece of code, let's say. After S1 is over, I'm starting the async. So this S2 and S3 will run in parallel, and both will wait here because this is a join point. Okay. After both of them reach, after S2 has finished, S3 has finished, then we will go and execute S4. Is this idea of finish clear? Or any questions, anyone?
So I have a question. So when you say async a statement, so is there a distinction between if it is run concurrently versus parallelly? Because if you run concurrently, it doesn't have to run in a multi-core system. It it depends on the scheduler, right? But in parallel, it should run in parallel.
No. Again, it's not that it must run in parallel. It may run in parallel. So here it says in this S2 and S3 may run in parallel. Why do we say may run in parallel? Because let's say you have only a single hardware core available, then even though there are two parallel tasks, the runtime may say, hey, don't create so many tasks. Okay. Makes sense, right? You don't want to create too many parallel tasks. So we'll leave it to the programmer, doesn't have to worry about it. Correct?
Thank you.
Okay. Any other question?
So with this syntax, how would we represent? Let's say I would have another statement S4. And I want that to be in async. So like, would you just put it in the async block like along with S2, or would it be another like async and S4?
So it depends. What do you want the code to run in parallel with? Do you want that code to run in parallel with? Do you want that code to run in parallel with the S2 part, S3 part? So let's say, so I have this code, right? Now within this async, I can have, I'm just making it S2 maybe one more async I can have, my wish, S22, S23, and then I have, let me add one more page here, and S24. Right? So this S21 will may run in parallel with S24. S22 may run in parallel with S24. S22 may also run in parallel with S23. S23 may run in parallel with S24.
Okay.
But S21 happens before S22.
Got it.
You can find similar constructs in other parallel languages as well. OpenMP has its own tasks and all that if you want. Is that fine?
Yes, thank you.
Okay. Any other question? No? Okay. Okay, let's continue. We'll use a very, once in a while, we'll use a small shortcut saying that for all. What is for all? It's nothing but a for loop in which I create n asyncs and there is a finish outside. Okay, just a syntactic sugar I may use, a shortcut. So this is like a parallel for loop. Rishik, you had a question, is it? Rishik Ra? No, okay, maybe not. All right. Okay, let's continue. See, one question to remember, one point to remember, just because there are n asyncs doesn't mean at runtime you will have n parallel threads. Right? Because you may create, I may have a loop over a million iterations. Creating million threads is, may not be prudent at all, right? So, the programmer says create as many tasks. I mean, he says, okay, create a million tasks. But at runtime, you may say, hey, they're all parallel tasks, but I don't want to run them in parallel. If I have a machine with 4 cores, maybe divide the million tasks into equally among maybe all the 4 cores. So and create only 4 threads. Is this idea of tasks and threads? You have each thread which can run multiple tasks. Okay, tasks are like jobs. Like, yeah, I want to cut vegetables. I want to wash vegetables. I want to set my books. I may want to clean my cycle. They are all different tasks. But let's say only 2 of you are there as roommates. Then the runtime threads probably is 2. Am I making sense in terms of number tasks and threads? It's an important distinction. Anyone not clear with it about it?
So can you repeat?
Yeah, so when I have many threads are the workers. So instead of looking at threads and tasks, we can use the word workers and jobs. Workers are active entities, right? They do the work or they do the jobs. Each async creates a parallel job or a parallel task, job or tasks, right? Or works. A worker or a thread is the one that actually does the work. So you can have many tasks and a much smaller number of workers. The workers will share the work among themselves. Am I making sense?
Yes, sir.
Okay, great. Let me. Anyone else has any other question before we go into the more fun part?
Sir, how is the tasks divided into the threads? And when we are dividing, when let's say we have a worker, we have assigned some number of tasks to the thread. So how is the serial decided? I mean, which task will be executed first? Is it
right?
Yeah.
Yeah, Prerana. So this is a very important question. Given a set of jobs, how do you divide the work among the workers, right?
Yes, sir.
I mean, in general, it's a very difficult problem to solve. There are many solutions that have been proposed. Typically, it is left to the runtime, which may take some input from the compiler to decide which worker gets what job. Okay, so that is called scheduling. It's a very important problem. Even under restrictive scenarios, it's an NP-complete problem. Optimal scheduling. Okay.
Okay, sir. Sir, you I did not understand. You were talking about someone asked this question about nested async. So it was. Could you please help me understand? I mean, what would nested async mean? I mean, like which task completes before what.
Right, let's do that. For the heck of it, I'll put one more finish here. Async S4, S5, perfect. Async. So I have finish here, let us say. So whatever starts here must end here. In this, whatever starts here will end here, okay? So let me draw the task tree. So let us say there is a statement S0, which I finished executing, and then there is a parent task. I'll call it the parent task which is executing the finish. The parent task first executes S1. Then there is async S2, right? Within this async. So let me see where does it close. Okay, so this async closes here. So inside this async, a bunch of things may run in parallel with whatever is coming after the async. So S6 will run in parallel with whatever is inside. Let us look at whatever is inside here. Here, first thing I will have is S2. I'm just expanding this triangle here. Okay. So I'm writing S2. And after S2, I will execute S3. But remember, this S3 is inside an async. So I will execute this async. And this, inside this async, I have one more this thing. So this guy, if after this async there was a statement, this and this will run in parallel. Inside this triangle again, I have an S3 and finish. So after S3, this finish will start. Inside this finish, I have a S4, async S4 and S5. So S5 and S4 will run in parallel. So these two will run in parallel, and then they will wait for each other in the finish. Okay. Now you may say, what about S6 and S4? Of course, S6 is running in parallel with the whole of the triangle. So S6 can run in parallel with S4 and S5 as well. Okay. It is simple. It's a simple tree. This thing. So I have a tree. I'm creating tasks. Okay. Let's say inside this finish, if it is finished, under it, whatever is there, they may run in parallel with each other, but not beyond that. And if it is an async, let's say this is an async S1 and S2. So I'm creating async and going down here. Then this S1 will run in parallel with whatever may happen after that. Okay. We will stick to some simple concepts. So here, if you look at it, after in iteration 1, one async is created. It will run in parallel with iteration 2's async, iteration 3's async, and so on. Okay. And they are all, this finishes up for the whole block. Okay.
Is it mandatory to have a finish at a root level, or it's perhaps not?
Let's assume in this language, let's assume if you don't specify a finish around your main function, let's assume there is an implicit finish. Okay. The programmer can also specify a finish. Finish is a join statement. This is a task create statement. Right? Yeah, go ahead.
What I was asking is, like, conceptually in programming, is it mandatory to nest everything into a finish, or there is also
it's a good programming practice to do so, and most languages either explicitly or implicitly enforce it. Okay. Any other question? No? Okay. Let's have some fun. Let us say I have some code. I have a for all loop, P going from 1 to n, and I'm executing S1. Okay. And remember, this for all loop, which is a parallel loop, is executed twice, once for iteration 1, once for iteration 2. Okay. Let us say in iteration 1, and let's say I have total 4 threads. And like some of you asked, if I have n iterations, how will the threads share? Let's say the runtime somehow shares the work. Maybe first n by 4 iterations to Piyush, second n by 4 to Pradeep, next for n by 4 to Prerna, next n by 4 to Rishi. Okay. And let us say the way the work and the same iterations are divided again. And let us say this is how the work looks. In iteration 1, thread 1 does 30, 20, 30, thread 2, 20, thread 3, 25, and thread 4, 10 units of work. How do you measure the units? Some units, time if you want. Okay. And if you look at it, after the first iteration, all the tasks get over, only then the second iteration is starting. So that's a barrier. And then in the second iteration, I am executing again the same loop, but now thread 1 gets the same set of iterations. Even then, thread 1 may be doing less work. Now do some simple math and tell me the total work done by thread 1 and thread 2, thread 3, thread 4 are all equal. Now we have ensured by this, the runtime has ensured that overall the work done by each thread is equal. Okay. Work done by each thread is equal. How much time will it take to execute this whole code? How many units of time? Anyone?
100.
100. Why did you say 100?
Because there's a barrier in between, so everybody will have to.
Everybody has to wait, all right. But
Yeah.
T1, T2,
Sorry,
T3, coming
30.
400.
Yeah, 30 and 40, 70. I'm sorry.
30 plus 70, assuming
30
the barrier time we are not calculating. So it is total 70 units of work.
Yeah, 30 plus 40.
Their total work done is only 50 units, but the time taken is 70 units. Overall, they have equal amount of work, but in parts it is unequal. Right? So the point is, overall equal work doesn't necessarily lead to balanced load. Am I making sense? Anyone having any questions? No? Okay. Instead, let us say, see, instead of saying like this 30-20, I mean, here the issue was because of this barrier. Because of this barrier, T1 had to wait. T4 had to wait for T1 to finish. If this barrier wasn't there, then I could have executed T1 for both the iterations, then T2, then T3, then T4. That's a cool idea. If the barrier is not required, I can move the for all outside. What is here the for all doing? It is only creating 4 tasks, okay? And in each task, I will execute the whole body by dividing the work so that each one is getting n by 4 iterations. How that actual division is done is a simple math. That's not interesting at this point. What is more interesting is that I have moved the barrier from inside the for to outside the for. What's the food for thought? We need to think as a programmer or as a compiler how to find the imbalance across iterations. And once we find the imbalance, how do we balance it? Question is, can the process be automated? Okay? And can some tools help? Remember, it's not always easy or trivial to remove such a barrier. What if thread 2 depends upon thread 1 and thread 3 depends upon thread 2? In such a case, we have to wait. Okay? So safety is important. We have to take care of the dependencies. Okay? Because if you don't take care of dependencies, it may so happen thread 2 will start executing before thread 1 finishes. And that would be incorrect. So for our first programming pattern, the moral of the story is, as a programmer, it's important to think in parallel. And in the compiler, while it's when it sees such a code, it can try to parallelize. Okay, because balancing the workload among the threads is important. Okay. Any questions? I'll just switch on the lights and come. Yes. The pattern and the issues. Any questions? Let me go back to the pattern and keep it there. If you don't understand, I can go over it again. We can keep it as a more. It's okay if I don't cover a lot of slides. I'm not for that. Let's have some interaction. Anyone? Any questions? No questions. Is it clear, everyone? I wish this was an in-person lecture. It would have been more fun.
Yeah, it's clear to me.
Okay. Thanks. Is there a chat window here? Anyone knows? There's a chat window.
Yes, at the top right, you can see a chat bubble near to the participants. So you can.
Participants. No, I'm just wondering if someone wants to just say something over the chat window, if it's possible.
Yes, if somebody's saying, I'll read over to you.
Okay, great. Yeah, sure. That'll be great. Thank you. Let's continue then. So we looked at the first pattern, okay? My goal is to show similarly such patterns and excite you about this. I mean, for a how such patterns, what type of patterns do we find and what challenges do they pose? Okay, here is another pattern. Okay, here is another pattern. Let's say I have a function foo which is called by bar, and inside foo I am calling foo recursively twice inside a finish. Okay, so if you look at this thing, foo will call 2 asyncs, and each async will again call further asyncs in a recursion. And there are finishes around. So if I have a nested, I have a deep nesting, I will have many such barriers. What if I move this finish outside the foo? Look, in the previous, in the original code, I had a foo. Wait, I had a foo. Oops. I had a foo which created one finish, which in turn called async foo twice. So I'm just showing foo again. And again, this calls finish. And so on. So basically you will see there's a tree of finishes. One finish calls 2. Each finish calls 2 each. So many barriers, so many joins. And as we said, joins are expensive, right? Would it be, I mean, let's think what would happen if we move this finish outside. There is a single finish. Inside that, I have the full recursion. So the number of barriers is much lesser. Yeah. The main points to keep in mind here is that we are talking about recursive task parallel programs. They are not traditional simple parallel programs, they are recursive. And not all joins or finishes are required. All right, then this natural question to ask is how to identify either finishes which are useless or independent finishes. Okay, if there are finishes which are dependent on each other, we cannot also remove. Here is a simple piece of code, right? In terms of whether they're useless or not. Let's say I want to compute Fibonacci. Okay. I want to compute Fibonacci n-1 and Fibonacci n-2. Let us say I compute them in parallel and store it in V0 and V1, and I return V0 plus V1. And let's say this fib is called from somewhere main as n equal to fib. So now what I'm proposing move this finish outside the first call to fib and let fib do these two things in parallel. Do you see any issues here? Anyone?
So when you're trying to write to v of 0, fib should have completed by then, right?
Exactly. See, I have created a parallel task. I have created another parallel task. These two will run in parallel with this return statement. As a result, I may be reading V0 and V1, which is stale.
Right.
So it may not be safe, right? To extract this outside a recursion is a non-trivial across a function boundary is a pretty complicated task. We have to be careful about the correctness part. So we want to keep the cost of parallelism in mind and see where we can reduce the finishes. At the same time, the dependencies are important. Okay? Any questions on the second pattern, where we said if there are joins whose scope can be expanded, we should do it. Okay? Ideally, a compiler should do it.
All right. Only if you have, if the compiler can see the, this call graph, and only then it can do that optimization, right?
Oh yeah, I mean call graph is one of the kind of the first things we need, right? But that's not enough. We have to know the dependencies, right? I mean, if you just go back in the previous code, the compiler has to figure out that if you move this finish outside this, then the dependency will be violated. There is a write, there is a dependency from this write to this read, isn't it? If you move the finish, the dependency doesn't exist anymore.
Right.
So in essence, it's not just the call dependency, but the data dependency as well.
Data dependence, absolutely. So when I said data dependence here, what I meant was data dependence. Control dependencies, both. Data and control, both dependencies. Any other question? All right. Let's go to one more pattern. Okay. Let us say I have the following code. I have a parallel loop which creates n tasks, right? All the n tasks are doing the same, executing the same code. So now, is it safe to say that all the n tasks will execute the same amount of work? Pay attention to my words. Same code and same amount of work. What do you think? Anyone? It's a small group. Let me randomly pick people. If that's if that won't be considered rude. Kaushik, what do you think?
Yeah, I think it might not be necessary. It depends upon the problem we are trying to solve.
For example,
for example, if we are trying to do a DFS of a graph, and each node we parallelly allocate them to find who are their neighbors. So some nodes might have 100 neighbors and some nodes might just have 10. So
excellent point. Excellent point, Kaushik.
Answer that. Yeah.
Excellent. I mean, let's say you are processing the Twitter graph, right? And I give you 2 nodes, and let's say there are total only 4. I mean, we are only interested in 4 nodes. I'll give you 2 nodes. I'll process 2 nodes. Just as the nodes I give you to work are that of, let us say, Modi and Trump and Obama, and the nodes I process are, let's say, that of myself, you, and Piyush. And I'm assuming none of us are anywhere close to that, right? So you will keep on working forever, isn't it? Because the number of neighbors is very different. The Twitter graph, I mean, if you look at, there are, so every vertex is not equal, or every iteration is not equal. Okay. So now what we did, every time we create so many tasks, right? The tasks are divided among threads. This is how the division was done in one particular execution. 0 to 7 threads got this, and 8 to 15 got this work. So the execution, so y-axis shows the normalized execution time of every thread. So the number 3, which is the highest, has 1, the rest have less. Okay. Now look at it this way. Does every thread has equal amount of work? No. The threads have unequal amount of work. I'll tell you something more. In this particular hardware, I had total 16 cores divided into 2 sockets. 8 into 8 plus 8. So this is socket 1, this is socket 2. So it may, so now it looks as if both socket 1, which has T3, and socket 2, which is T8, both will execute till, both will have threads executing till the end. Okay. See, if both T3 and T8 are in two different sockets, I cannot even reduce the frequency of one socket because both of them are executing, both of them have the same critical length. The critical length of S1 and S2 is the same. On the other hand, let us say I move T3, T8, T11, rather T8, T11, which are the heavier ones, and maybe even T15 to S1. Okay, these three I move to S1, and the smaller of the S1s, let us say T2, T4 and T7, I move to S2. What will happen? S2 can actually finish faster. The threads of S2 can finish faster. Threads of S1 will not take any extra time. Now I can switch off S2 if I want because S2 has finished executing. How cool is that? I'm introducing imbalance because if there is imbalance, I can do socket-wise optimizations. So I will say this S1 is a socket which will do more work. S2 is a socket that will do less work. I can even run S2 at a lower frequency. So if I can identify how much work may be done by each thread, I can move the move all the heavy running threads onto one socket and the slow running, less work threads onto one socket. Right? And then I can say on the second socket, run it on lower frequency, let it consume less energy. Is this idea clear that only because of this critical path, both T3 and T8, which are on two different sockets, neither of S1 and S2 can be slowed down. Otherwise, your overall program will take more time to execute. But if you take all the threads which are taking more time and put them in one socket, and the threads which are taking less time, put them on the other socket, I can kind of either finish work early and go to sleep. That's also a possibility. Right? Am I making sense? Such problems don't exist in serial codes. So, important point we are talking about is task parallel programs with irregular loops, where the not all iterations have equal amount of work, and we cannot statically determine that. And the important question is how to group these iterations, how to group these threads, iterations onto different threads, and threads onto sockets in a multi-socket, multi-core system. Okay. Remember, there are efficiency issues. Migrating threads from one socket to another can be expensive. How, when you say, hey, I will reduce the frequency, how much will you reduce? If you reduce the frequency too much, then S2 will run much slower. Okay. I will tell you something. I will not tell the answer, but in such a scenario, it may so happen that let's say I have these two sockets S1 and S2. I am slowing down S2. I am slowing down reducing the frequency of S2. It may so happen I may end up reducing the performance of S1, or S1 may take more time. Again, I repeat, I reduce the frequency of S2. But I have slowed down the execution of S1. How cool is that? Can anyone guess, just for the heck of it, how can reducing frequency of one block reduce the execution time, rather increase the execution time of S1.
Could there be a dependency between the tasks scheduled across both the sockets? So maybe one task which was scheduled on S1 that depended on S2, but now since that S2 task would take more time, so
Brilliant, brilliant. What's your name? Joso, is it?
yeah, that's just.
Am I pronouncing it right? Zoso?
Yeah, that's just my nickname I've used for all that.
Okay, that's fine. So Zoso, you're absolutely bang on target. Let us say S1 does something and then waits for S2. If S2, which was initially running at full speed, probably it would have finished here. But now at a slower frequency, S2 probably takes so much more time, and now S1 is delayed. Right? So this is, I mean, absolutely a brilliant scenario where even though I'm reducing the frequency of another independent socket, I'm some other socket is slowing down. Right? So moral of the story is we have to keep the energy costs in mind, and there are hardware provided support for energy reduction that can be used. Okay. Let me ask a question to our organizer. How much time do I have, Pradeep?
So we are at 6:34 right now. We can spend more 15 more minutes.
10-15 minutes? Okay. Okay, we'll do that. Here is one more programming pattern. Okay. The same type of code like before. I have a for all loop and I'm going over all the neighbors. But just a additional catch. Just an additional catch. In every iteration, it's not that I'm going over all my neighbors. A typical code that you will find in many of these graph analytics is like this. In one round, I will iterate over every vertex. Okay, first round, or maybe some set of vertices, and then I'll mark some of them as active. In the next round, I will only process the active vertices. And again, some of those which I'm processing, I may mark them as active equal to true, and whatever was active may be marked as not active for the next round. How cool is that? In such a scenario, how to figure out what is the cost, right? So first of all, cost of processing each vertex is not the same. And then an additional challenge is cost of processing a vertex is not same across rounds. How do we deal with it? We cannot say, okay, in every round, I will bring all the active vertices next to each other and then process, because reorganizing the data can be expensive. We are talking about kind of gigabytes, terabytes, petabytes of data, right? So the point is, statically, we cannot reason about load balancing, that we agree. The load balancing requires runtime analysis. But if you do a lot of analysis at runtime, you will end up paying a lot of execution. I mean, if you while executing, you can do some additional analysis, but that will slow down your program. What do we do? The best tactic is use a combined static and runtime scheme. Use static analysis as far as possible, and then at runtime do very little analysis. Okay. Any questions? Now? Yeah, go
Problem
ahead.
with graphs in general is the architectures that we're talking about are optimized for data
SIMD
local pattern, SIMD and all
data
that.
parallel.
Data
Absolutely.
parallel. Right, but graphs are very different because they are irregular parallel programs, and is it really useful to discuss optimizing graph in the current architecture instead of inventing our own irregular processing unit, something like that?
See, Pradeep, if we get some such processing units which can speed up graph analytics, great. See, what's happening is the following. Should I not analyze graphs? I don't have that option as a compiler. Should I not compile graph analytics? As a compiler, I don't have that option. As a programmer, should I not write graph analytics code? I don't have an option because my client wants it. If you look at some of the large, say traffic processing, if you look at gene processing, many of these weather modeling, they're all, if you want to analyze social networks, if you want to analyze many of these current big data apps, right? They are all irregular. What to do? As a programmer, you have to write irregular programs. As a compiler, you have to analyze them. Unfortunately, the hardware is not in a position to handle them well. So that's where the compiler comes. See, as a compiler writers, right, you should be happy when either the hardware doesn't have the capabilities or the language doesn't have the sufficient power. That's where the compilers come into picture, isn't it?
Yeah, it's a cool work for a compiler.
Right, because we have work, we have job to do. But you have a very important question, right? When we have things which are irregular, the current hardware, if you give it to a fully data parallel system, right? Every iteration can run in parallel, but most of the parallel threads have no work to do because let's say I have only 2 iterations which are active. Every thread comes, looks at the if active, if it is false, it will just wait for the other threads to complete. Not a great scenario, right?
Right, yeah.
So it's an amazing. If those of you who work on such either such compilers or such hardware, it's an amazing place to be in because these graph analytics present problems that are absolutely not seen before. Totally hairy. You'll kind of really pull your hair. If you ask, is this real hair or plastic? I won't answer that. But yes, it's an amazing. Even my experience in this has been absolutely fabulous because the problems are just very challenging. I'll do one thing. There is at least one more pattern I wanted to talk. I'll skip that for the time being. Instead, I will go to our overall morals. Okay. Parallelism in the program. When we want to think in parallel, we have to keep in mind that the logic can be parallel. You can create as many parallel tasks because that's what the program logic could dictate. But that could be different from the runtime parallelism. So the ideal parallelism, which is given by the program logic, and the useful parallelism probably dictated by the hardware and the runtime. The hardware and the runtime may say, look, I have only 4 cores and hence 4 threads. So that's a useful parallelism. We want to avoid creating redundant tasks, redundant joins, useless joins. We have to be careful about very serial part, very parallel part, because at some level the Amdahl's law will come into picture, and if there is the serial part can become the bottleneck and all that. And one thing that I have skipped is analysis, the dependence analysis, the point tree analysis, any analysis that you are doing. Remember that analysis is not sufficient for parallel programs. You need MHP aware analysis. Okay, that's a very interesting topic in itself. I can talk about it for a full long talk. Okay. So if you are using traditional analysis for parallel programs, unless you are careful, the analysis could lead to unsound results. Okay, so that's all about thinking in parallel, both from a compiler point of view and a programmer point of view. And when you are parallelizing, we have to keep the cost of parallelism in mind. Okay. There are many other patterns that we have not covered that cover locality of data, locality of patterns, computation, how to find redundant barriers, redundant computation, redundant atomic or critical sections, and this it's a big list. Okay. You may say, should this be done manually or automatic? Ideally automatic. Okay. And there are tools, including the work done in our own lab, where such optimizations have been developed and are being developed. We are also working on language extensions to improve performance and programmability. And we work on, we also work on traditional languages optimizations and analysis. So this is kind of a quick self-drumming. Okay. If you are interested, do visit our website to get more information. Okay. I mean, I'll just quickly conclude. I mean, task parallelism is the mantra of the day. You don't have an option. Wherever you go, you have to work with parallel programs and parallel languages. Okay. Obtaining efficiency in parallel programs is a beautiful challenge. It's unavoidable though, but it's lovely. Okay. Parallel program analysis is a very exciting area for research and work. And optimizing parallel programs has tons of problems to look at. Right? If those of you think, hey, why bother about it? Look, we are not able to utilize our current petascale computers. We are touching exascale, and people are already talking about zetascale processing. Are we ready for it? Are we, as in the programmers, the language writers, the architecture designers, the compiler writers, as a group, are we ready? Right? If you have questions, I'll be very happy to take them. You're also welcome to write to me. Questions, if you have more.
I had one question regarding the finish thing. I think the thing that I brought up between. You said it's a good programming practice to have one global finish at least.
Oh no, it's not a question of programming practice. So the question is it a good practice to have only one finish per program? The answer is not a question of practice. It's a question of requirement. I'll go back to this small piece of code we had seen. Let me just, yeah, in this code, I must have a finish here. Let us say this Fibonacci is called many times. Let's say I have a loop. Let me write here. Let us say I have a loop for I goes from 1 to n. I want to call Fibonacci many times. This again can go in parallel, async fib. But inside the fib, this must happen in, I mean, this finish must be present. So I can have a one finish here, and then I can print that work done. So the program may require that you have multiple join points. Rishik, do you see? It's not a question of it's a good programming practice. It's a good programming practice to keep minimum finishes. That's good for efficiency, but not necessarily one. There are times when you cannot avoid finishes. Am I making sense? Rishik?
So it's actually some other person who asked.
Oh, sorry.
Girish, I just considering because I don't a little bit parallel programming I've done, but basically I'm just thinking like if you're doing something like let's say you want to run a daemon thread or server, right? A daemon thread is I think it's a classic case of something which you wouldn't want to envelop inside a finish.
Absolutely. No, not sure. Here is my code, right? Here is my, let's say, pick your sendmail D or whatever, some daemon, right? Girish asked the question, I guess. Now, so right. I'll make a server called Girish D. Okay, and in Linux or whatever, you may invoke some Girish D start. When you do Girish D start, it will invoke the loop. Okay, this loop is a thread that will run forever. But it may so happen that in this loop, you are catching an interrupt that says stop. Catch stop interrupt. Then you may want to clean up and then die. Okay, and after dying, you may say after the thread, you may say I'm done. I've done cleaning up. I'm done. So it depends on the program. It's difficult to say when you don't want to have a join. Ideally, I think if you ask me, I will say you must have a join at the end of your main so that you have cleaned up whatever you have done, mess you have created. You may be a long running program, that's fine, but the program can run in the background forever. That's fine. Okay.
Got it. Yeah, sure. So basically, it's about the ownership of having the resources that you eventually either you do it or the JVM any runtime will take care of
or
it.
the runtime does it. Yeah, sometimes the runtime the language says, look, it's implicitly done. That's fine. That's a separate issue. Any other question?
So I have a question on. So what do you think about just-in-time compilers for graph processing? So in the case that you explained in the last example, where you have a for all loop and you have an active set to work on, or frontier set of active nodes. So let's say you have a number of threads equal to true. Now the JIT compiler can come in and optimize. Say, okay, you have 2 threads. You don't even have to do it. Two in parallel. You can just say, yeah, do the 2 in serial.
But how will the JIT compiler know? It's a very good question, right? So what you're saying, can the JIT compilers be aware of such notions of active nodes and then do something specific for those? It so turns out, whether it's JIT compiler or not, identifying which nodes are active is not trivial either. Right? You need to know understand the program that, hey, based on this is a flag based on which most of the computation is being done. Okay, so currently the JIT compilers don't do it. If you are asking that, can the JIT compilers do something smart? I think in theory, yes. Yeah, at this time, no, we don't know any smart things to do. But I think that's a very interesting thing to explore. All right. Thank you. Thank you for your questions. Thank you for your time.
Okay. So since there are no questions, we can. I think somebody's typing in the chat. Okay. Okay. Since there are no questions, I think we can end the meeting here. So thanks, Krishna sir, for this enlightening talk and providing us, an exciting, new topic to think about. And it's very exciting for compiler writers to solve this problem. Yeah. Thank you.
Thank you very much. Bye-bye.